Everyone stopped talking when I put the microphone on. That was interesting. Because you know it's going to pick up everything you say. That's right. All right. So I graded question 1.2, number 4, which was asking you to show that certain properties were true. One thing that I commented on, I didn't deduct for it, but it said the universe for all these questions was the integers 1 through 9. And a lot of people changed the universe, which is okay for this. But if you can change the universe, I guess you may as well. So let's see. So A subset B, B subset C, therefore A subset C. I think we actually did this a few days ago, but here's a simple example. A equals 1, B equals 1, 2, and C equals 1, 2, 4. Oh, yeah. All these details, man. All right, so A is 1, 2, A is 1, B is 1, 2, C is 1, 2, 4. Clearly A is a subset of B, and there's nothing to really prove that. You can just sort of state it. And B is a subset of C, and A is a subset of C. So that demonstrates what part A was trying to show. And then part B was asking you to prove that in some cases, A take away B is not equal to B take away A. So the first thing is to understand what this minus means. It's not subtraction in the arithmetic set. Okay, A minus B we can write as A complement B. It's the complement of B in A, which is the set of all elements in A which are not in B. So we're pulling out elements from set A if they belong to B. So most any sets will verify this identity. For example, A could be the set 1, 2, and B could be the set 2, 3. So A take away B is start with A and throw away anything you find in B. Well, 2 is in B, so we throw 2 away, but 1 is not, so this is just the set 1. Whereas if we start with B and we throw away A, we have 2, 3. We don't have to throw away 1, but we have to throw away the 2. All we're left is with 3, and so those are not equal sets. So part C said that suppose the universe is the union of A and B, and suppose that the intersection is the empty set. I practiced writing the universe symbol last night, can you tell? The intersection is the empty set. Then A is equal to the complement of B, which is just the universe minus B. So an easy example might be A equals 1, 2, 3, 4, 5. B equals 6, 7, 8, 9. And you got to show what the sets are if you're going to show that this equality is true, right? So this is what A and B is, and it doesn't hurt to say A union B equals, and just show the union. And then state that the intersection is the empty set because there's nothing in A that's in B and vice versa. And then show that the universe take away B equals, well, it's all the things in the universe 1 through 9 minus 6, 7, 8, 9. That just leaves you 1, 2, 3, 4, 5, which sure enough is equal to A. So again, we're not proving, but we're demonstrating an example of this equality or an example of this inequality. And then part D can get a little cumbersome depending on how you pick your sets. So part D, you're trying to show that these two things are equivalent. Well, anytime you're doing cross products, your sets are going to grow. And if set A has 5 elements and set B has 6 elements, the cross product is going to have 30 elements. So you probably want to pick small sets to work with this, but not so small that they're uninteresting. I could take the empty set for A, B, and C and show that this is true, but do something a little more interesting. So I'm going to set A equal to just the singleton set 1. I'm going to set B equal to 2, 3, and I'm going to set C equal to 3, 4. And we do this kind of like a proof, even though we're not using the formalism of propositional logic. We want to lay this out step by step in a way that makes it clear what we're doing. So I'm going to start off by finding what B intersect C is. And the intersection of these two sets is just the singleton set 3. And so now I can say A cross B intersect C is equal to the singleton set 1 cross the singleton set 3. And what's that going to be equal to? It's a set containing the single tuple 1, 3. That's the only way we can form a tuple where one element comes from here and another comes from here. So we've got that. Now I'm going to calculate what the right side is. So A cross B, this has 1 element, this has 2. I better end up with 2 elements, and in fact I do. It's the ordered pair 1, 2 and the ordered pair 1, 3. And then A cross C is this set crossed with this one. So it's the ordered pair 1, 3 and the ordered pair 1, 4. And now I'm going to intersect those two sets. And the only thing in common between those is just this one element, the ordered pair 1, 3. And that is exactly equal to A cross B intersect C. So that's a demonstration of that property. I'm looking at my notes of things I saw that raised questions. So the idea here is to be showing your work, right? And just like when we're doing formal proofs, you got to be a little careful. So prove, or let's say show, A cross B intersect C equals A cross B intersect A cross C. If you start writing stuff over here equals stuff over here, you got to be a little careful with that. If I write this over here, right, so I say something like 1 cross 2, 3 intersect 3, 4 equals 1 cross 2, 3 intersect 1 cross 3, 4. I don't have a right to state this yet, right? What I'm trying to do is demonstrate that this is equal to this. I can say that this is equal to this, and I can say that this is equal to this, but as soon as I write down that this is equal to this, I've written something that I haven't shown yet. And it becomes really confusing what it is that you're actually demonstrating versus what's the derivation up to the punchline. So I wouldn't write that. I would write something like this equals that and this equals that, right? But write the equals horizontally, right? So just be careful of that. Keep that in mind that if you say something equals something, you either need to defend that or you need to make it clear that this is an assumption, right? So, and over here, the only things we wrote were equal were things that we had definitely shown were equal. We defined A, B, and C. We said that B intersects C equals, and we calculated the intersection. And then we crossed with A so we could say this equals this. But it's only at the very end, once we've shown that this and this have the same value, that we can say this equals this. So just be mindful of that, because we're going to go back to doing proofs pretty soon. And that's a big catch you in proofs. Oh, the other question I had, I saw this on like 3 or 4 assignments. This was for part A. So people defined what A was and what B was and what C was, and then they said A is a subset of B, B is a subset of C, A is a subset of C. But then next to that, I saw the following. B is greater than or equal to A. C is greater than or equal to B. C is greater than or equal to A. And I don't know what that means. If it's something I wrote and I was trying to write the subset in the other direction maybe or something. But we don't have a greater than or less than or greater than or equal sign defined for sets, right? We have this subset symbol, and we can write that subset symbol in the other direction, right? This is the same statement as this, but traditionally we write it like this. But if we have something and we want to say there's a subset, we could write it like this. But I'm not sure what that means, so if anybody wants to tell me, that's fine. That could be. So this is definitely true.
Like a lazy kind of C shape, like instead of rounding it out.
Yeah, it could be that it meant to be like this, but it was definitely greater than signs. And like I say, I saw at least 4 homeworks that had this, and the same thing, these 3 written like this, and then right next to it those. So anyway, if there's some confusion there, feel free to ask me about it. So any questions on any of the homeworks from that? So make sure that you've, because that's the only question I really looked at in detail. So if you're not sure you did the other questions right, make sure you ask. So I posted your next homework, number 3, last night, and it's mostly, I think it's all from chapter 7, which is about functions, which is what we started talking about a few days ago. I'm going to talk more about functions today. So eyeball that, bring questions next week, right? Monday preferably. But we should be through everything that you need today in order to do the next homework. So functions, remember, we could say f was a function from a to b. It meant that for each element a in a, we had some element in b, which we can write as f of a. So we can think of f as taking a and changing it into some element of b, which we call f of a. And you can always think of a regular function f of x equals x squared. That's a standard example to go back to. But sometimes, and I mentioned in the homework, there's a spot where they do this. We write a function as a set of ordered pairs, right? Remember, a function is a subset of the power set of a cross b. So the function f of x from z to z let's just say f goes from z to z, f of x equals x squared. We can express that function as a collection of ordered pairs, like so. And this is clearly a subset of the power set of z cross z. Right, each of these things is an element of z crossed with itself. But the way I've set this up here is that this contains all the ordered pairs where the first element is a member of z and the second element is f of that first element. So it's the square of the first element. And so if we were graphing, this would be a set of all the points on the graph. 0, 0, 1, 1, 2, 4, negative 2, 4, and so on. So in the book, there's some questions where they ask you to list the members of a function. That's a way of saying, write out the function like this. Show all the ordered pairs that correspond to the function. All right, well, things we can do with functions. So suppose we have two functions, f1 and f2, from a to b. We can define a new function, f1 plus f2, which also goes from a to b. So we can add functions together and get new functions. And what this function does, if we apply it to some element x, is the following. It calculates f1 of x, it calculates f2 of x, and it adds them together. And this only works if addition is defined in the codomain B. So if we're thinking of, say, integer to integer functions. So f1 plus f2 is a function. It takes an element of a and it gives you an element of b. And the element it gives you is the sum of f1 and f2. So for example, so f1 goes from z to z. f1 of x equals 2 times x. And f2 goes from z to z. And let's say f2 of x is equal to x minus 5. So f1 plus f2 is a function from z to z. Which takes an element x and it maps it to 2x plus x minus 5, which is 3x minus 5. So kind of the way that you would hope addition works, right? You can just pull it outside and do the additions independently. And we can do the same thing for multiplication. f1 times f2 is just f1 of x times f2 of x. But we're doing arithmetic on functions themselves, right? Not on numbers. We're actually taking these two functions and adding them and getting a new function. And then we can multiply by another function and get yet another function. So we can do algebra on functions. It's a good thing to do, actually. All right, if f is a function from a to b, we can write f with an exponent minus 1. And this is a function from b to a. And it's the function that kind of undoes what f does. It's the inverse function. So let's make that rigorous. We need two concepts. First concept is the identity function. And we can just call this id. So the identity maps from some set A to itself. And it simply carries x to x for all x inside the domain A. So the identity is a boring function. Just takes a number, maps it to itself. If we have integers, f of x equals x is the identity. Well, if we have geometric shapes, f of x equals x is still the identity. Takes a square to a square, takes a circle to a circle. It's boring, but it's critical. Okay, the other thing we need is function composition. So suppose f is a function from a to b, and g is a function from b to c. We can write a new function which is g little circle f as a function from a to c. So f goes from a to b, g goes from b to c. This new function will go from a straight to c. And the way we define this, if we take some element x, this is going to be equal to g of f of x. So we've got some point x over here in set A. First we apply f to it, which gives us a point in B. Then we apply g to that, which gives us a point in C. That's what this composite function does. So it's not multiplying the functions, it's saying do one and then do the next thing on the result of that first. Is that clear? So for example, let's just do everything from z to z. Suppose f of x is equal to x plus 2 and g of x is equal to x squared. So g compose f of x equals, well, first we take x and we map it under f, which gives us x plus 2. And then we take that result and we map it under g, which gives us this thing squared. Everyone got that? There's homework questions to work on these. So those concepts give us a way to define an inverse. So given f from a to b, f inverse from b to a is a function such that composed with f, we get the identity. And if we take f and compose it with f inverse, that maps from b to b. That's the identity. That's just a fancy way of saying if you have a function, you have an inverse, start with an element in set A, apply your function over to B, apply your inverse back to A, you should get to the same place you started. So f inverse maps back in the other direction. And in terms of pictures, if this is f, and it maps each of these points to each of these points, this is f inverse. And this is how identities work. If you take a point and you follow the function, you end up where you started. Now here's a classic question. Do identities always exist? Does every function, sorry, do inverses always exist? Does every function have an inverse? Why not? Well, any function, does any function have, so you're saying x squared doesn't have an inverse? Yeah, so f of x equals x squared. F inverse of x would be something like the square root of x, but it's not well defined. And the problem is, if we're going over all integers, here's the point 2, goes over to 4. Here's the point negative 2, goes over to 4. The inverse would somehow have to carry 4 to both 2 and negative 2, and that's not a function. Functions can only carry a point to one value, not to 2. That's the vertical line test in calc. So you can always write down what the inverse is, but sometimes it's not a function. Is there a rule for when an inverse exists? Function's got to be at least injective, possibly bijective. But this cannot happen, right? Different points have to map to different points over here. So we at least need injectivity. Now, if it's not surjective, right, if it's injective but not bijective, that means that there's some points over here which we're not mapping to, and so our inverse is not defined on those points. So if we have a function going from a to b, and it's not surjective, then we can't define the inverse on all of b. So in fact, you're absolutely right. F has to be bijective. And if it is bijective, then there is an inverse. All right, so some functions you may encounter in the homework and we'll definitely encounter later on in this course. One is the floor function, which maps from the set of reals to the set of integers. And we write it like this. It's kind of like square brackets without the top on. And this is the greatest integer less than or equal to x. And there's a ceiling function, which is the opposite. So what's the greatest integer less than or equal to 2.5? 2. What's the greatest integer less than or equal to 2.999? And what's the greatest integer less than or equal to 2? Still 2. But as soon as I get to 3, the greatest integer less than or equal to that is 3. And as soon as I get to anything slightly smaller than 2, the floor function brings me down to 1. And then the ceiling we write like this. And this is the smallest integer. Which is bigger than or equal to x. So ceiling of 3 is 3. Ceiling of 3.0001 is 4. Ceiling of 2.9 is also 3. So it's not rounding, right? Because ceiling of 2.1 would still be 3. It's not doing a regular rounding. It's saying if we just look at integers, how close can we get from above to this integer?
What a computer does when you put a float in for an int.
Yeah, maybe. It's always scary, especially with negatives. With negatives, if you convert it to an int, there's some ambiguity in what that's exactly going to do. If with floor or ceiling, it's unambiguous, right? Because, well, let's just do some negatives. So floor of negative 2.5. So what's the greatest integer less than or equal to minus 2.5? Right, because negative 2 is bigger. Ceiling of negative 2.5, smallest integer bigger than that. That's negative 2.
Is there like, there's no way to easily write just closest to 0?
Yeah. Do I want to prove this? Here's a weird function. F of n takes 2 times pi times n, takes a square root, takes n divided by e, and raises it to the n. Is that a function? Sure. It's well defined. Turns out this gets you pretty close to n factorial. And in fact, as n gets larger and larger, this gets closer and closer to n factorial. And in the limit, as n approaches infinity, this approaches exactly n factorial. Which is a little weird, right? Because n factorial is just multiplying a bunch of consecutive integers. This has got pi, it's got e, it's got square roots, and it's got n raised to the n. That's all kinds of mess. But it turns out to approach the same thing as just multiplying consecutive integers, which I think is pretty dang cool. So that's Stirling's formula. We're not going to prove that. I've never proven that, but there are proofs. All right, so good on functions. You remember injective, bijective, surjective? One-to-one onto and one-to-one onto. So informally, different x's go to different f of x's. That's what we mean to be injective. Surjective, everything in the codomain is f of something. So injective, different x's go to different values. Surjective, anything over here comes from some point in the domain. Something maps to it. Is that clear? Otherwise, I'll do my goofy cake slice definition, which I don't think helps. All right, so that's all I want to say about functions. So I want to switch gears again and talk about sequences and summations. And then we'll say a little bit about matrices. And then next week, we're going to go back into proofs. And we're going to look at mathematical induction, which is kind of the punchline of the course in some ways. Not that the other stuff we do doesn't matter, but it's the reason why I do things in this order in winter, because it's going to tie into what you're doing in CSE 222. Okay, mathematical induction will be key. So, but first, let's look at sequences. So a sequence is something like this. It's a set of values separated by commas. It's not a set. This represents the succession 1 followed by 2, followed by 3, followed by 4, 5, and then 6. It's a sequence of 6 integers. That's a finite sequence. Here's an infinite sequence. 1, 2, 4, 8, 16, 32, 64, 128, and on. This is a sequence of powers of 2, right? It goes on forever. But this is really a function from some subset of Z to some other set S. And it's a function from a subset of Z because these things are ordered, we can count them, just like we were doing with countable sets the other day. When you have a sequence, there's a first term, a second term, a third term, a fourth term. So f can be a function which maps the number 1 to whatever the first term is, and maps the number 2 to whatever the second term is, and so on. So a sequence of elements from S is the same thing as a function from some set of integers to that set S. So we can tie them into each other. All right, that's a good stopping point for here. So we'll start talking more about sequences, and that'll take us into recurrence relations next week. And then we'll go on to mathematical induction. All right, so I'll see you next time.